Hello, and welcome to General Astronomy Lecture 6, The Reason for Seasons. Now, in our previous lecture, we talked about some of the things we see from Earth in the night sky and how those things may vary in the night sky from, say, night to night or month to month. What we'll do in this lecture now is talk about one of the more drastic changes we experience here on Earth, that being the seasons. So we know that we have seasonal changes, such as longer and warmer days in the summer and shorter and cooler days in the winter. But why do we have the seasons? Why do they occur? Well, the reason we have seasons and why they are different in different hemispheres is that the Earth's axis of rotation is not perpendicular, or 90 degrees, to the plane of Earth's orbit. Instead, the axis is tilted by roughly 23.5 degrees from the perpendicular. So that perpendicular is this vertical line here that you see drawn. The axis about which we rotate is tilted 23 degrees from that perpendicular, or that vertical. And this is the cause for our seasons. Now, the Earth actually maintains this tilt as it orbits or revolves around the Sun, with Earth's north pole always pointing in the same direction throughout the year, toward Polaris. So, although we do spin on this axis, the axis itself does not really change. It's always pointing in the same direction as we move around the Sun. So as a result, at some parts of the orbit, say here on the left, the northern hemisphere is tilted toward the Sun. But as we move to the other side, half of a year later, the northern hemisphere is now tilted away from the Sun. This is exactly why we have seasons. So let's take a look at what happens when we're on the left of that image, when we are in the northern hemisphere tilted toward the Sun. The northern hemisphere spends more than 12 hours in the sunlight in this case. Thus, the days are longer, and it is summer in the northern hemisphere. The Sun is high in the sky, and so sunlight will strike the ground at a nearly perpendicular angle that heats the ground efficiently. So that's what this image on the bottom right shows. We have a sun that is almost directly overhead, so the sun rays that come down are almost directly going straight into the ground, which means that it heats an area fairly intensely, and we get efficient heating. So during the same time, however, in the southern hemisphere, days are shorter and nights are longer. Thus, it is actually winter in the southern hemisphere. So you can see that in the image at the top. The southern hemisphere is tilted away from the sun. So that's why it's winter. The steeper sunlight angle makes it summer in the northern hemisphere for two important reasons. So it's summer for two reasons. It's warmer because of these two reasons. First, as shown in this image here, the steeper angle means more concentrated sunlight, which tends to make it warmer. So we already discussed the first reason why it's warmer in the summer. We have concentrated sunlight that effectively heats the ground, or efficiently heats the ground. Second, if you visualize what happens as Earth rotates each day, you'll see that the steeper angle also means that the Sun follows a longer and higher path through the sky, giving the northern hemisphere more hours of daylight during which it is warmed by the Sun. So these two ideas might not be directly apparent, but once you hear them, it actually makes a lot of sense. We have direct sunlight and longer time being exposed to that sunlight. So those are the two reasons why it is warmer in the summer. Now, let's look at what happens half of a year later, when we are on the other side of the Sun. Half of a year later, the situation is reversed, with winter in the northern hemisphere, which is now tilted away from the Sun, and summer in the southern hemisphere. The Sun is low in the sky, so sunlight strikes the surface at a grazing angle, which causes much less heating. So you can see that in the bottom right image here again. So instead of the Sun being directly overhead like it was in the summer, it is now at some lower angle in the sky, meaning that when the sun rays hit the Earth's surface, they are not as direct, and so we don't have as efficient of heating as we did previously. During spring and autumn, so the two phases between winter and summer, the two hemispheres receive roughly the same amount of illumination from the sun, and daytime and nighttime are therefore of roughly equal length everywhere on the Earth. The sunlight angle gradually changes as Earth orbits the sun. It isn't just suddenly going back and forth between being a low angle and a high angle. In between these two extremes, both hemispheres are illuminated equally in March and September. It is therefore spring for the hemisphere that is on the way from winter to summer, and fall for the hemisphere on the way from summer to winter. Notice that the seasons on Earth are caused only by the tilt of the Earth's axis and not by the change in Earth's distance from the sun, which is one of the most common incorrect answers when somebody asks, what is the reason for seasons? So it doesn't have to do with distance from the sun. Although Earth's orbital distance does vary over the course of a year, right, because we know that Earth's orbit is elliptical, so the distance from the sun does vary a little bit. That variation is actually very small. If Earth did not have an axis tilt, we wouldn't have seasons at all. Earth is only about 3% further from the sun at its farthest point than when it is at its nearest point. The difference in strength of sunlight due to this small change in distance is easily overwhelmed by the effects caused by the Earth's axial tilt. So this slide is only here to kind of discredit that idea that the change in distance from the sun can affect seasons. It doesn't have any influence almost at all. It's negligible, is what we would say. All right, so the plane of Earth's orbit around the sun is called the ecliptic plane. So you've heard me say ecliptic in our last lecture. The ecliptic, again, is the circular path that the sun takes around the Earth. So you can see that in the bottom image here, highlighted in orange. That is the ecliptic, the path of the sun's motion in our sky. But the ecliptic plane is the plane of the Earth's orbit around the sun. So here is us in orange on the top image orbiting the sun. Well, the plane that orbit lies in is the ecliptic plane. And it's pretty easy to picture if you imagine hovering above the solar system, kind of like this 3D image tries to show. But it described quite differently when viewed from Earth. So it depends on where you're looking at it from. But the point is, again, that this is the ecliptic plane, just a term that you might hear once in a while. So, as a result of Earth's annual motion around the sun, it appears to us that the sun slowly changes its position on the celestial sphere over the course of a year. Right? So we are moving around the sun, but as a result, relative to us, it looks like the sun is moving across the celestial sphere. So that's what this is trying to prove here. The circular path, again, that the sun appears to trace out against the background stars is what we call the ecliptic. Because of Earth's tilt, the ecliptic is angled 23.5 degrees from the equator, which you can kind of make out in this 3D image. So here's the ecliptic plane here, and the tilt of the Earth's axis. So this angle right here between the sun and this axis is 23.5 degrees. Now, interestingly, since there are 365 days in a year and 360 degrees in a full circle, well, the sun appears to move along the ecliptic here at a rate of about 1 degree per day. Right? So 365 and 360 are basically the same number, more or less. So you get about a rate of 1 degree per day of the sun's motion in the ecliptic. So this is from west to east. Now, we're going to get into some specifics, and I just want to make it clear that this image here can become confusing, especially when you start working on some problems if you're in my class. We'll discuss it a little bit here on the next 2 slides, but it is an image you will come back to in your work, and you'll have to study it in a bit more detail than we discuss here. So do your best, and of course, you can always ask me questions as always. So, the ecliptic and the celestial equator. So the ecliptic is this yellow plane that you see, and the celestial equator is this blue plane that you see here. So the ecliptic and the celestial equator intersect at only 2 points. The 2 points you see labeled here as the vernal equinox and the autumnal equinox, which we'll get into in just a moment. These are exactly opposite to each other on the celestial sphere. Each point is called an equinox, from the Latin term for equal night. Because when the sun appears at either of these 2 points, day and night are roughly 12 hours long at all locations. They are equal. The term equinox is also used to refer to the date on which the sun passes through each of these special points on the ecliptic. For example, on about March 21st of each year, the sun passes northward across the celestial equator at the vernal equinox. So here's the sun, it moves around this ecliptic. Well, once you get down here, it starts to move northward and it passes the celestial equator in a northward direction, and when that happens, we have the vernal equinox. That occurs on March 21st. This marks the beginning of spring in the northern hemisphere, where vernal is from the Latin term for spring. Now, on the other side, on about September 22nd, the sun moves southward, so here's the sun moving southward, across the celestial equator at the autumnal equinox, marking the moment when fall begins in the northern hemisphere. Equinoxes occur on the 2 days of the year on which the sun rises precisely due east and sets precisely due west. The points on the ecliptic that are farthest north and farthest south of the celestial equator are known as a solstice, which is Latin for solar standstill, since this is where the sun changes its northerly or southward direction of motion. So these points occur here, the northmost point at the summer solstice and the southernmost point at the winter solstice. And again, it's called a solstice, which stands for solar standstill, because it is changing its direction. It's not physically stopping at these points, but what's happening is instead of moving northward, when you get to the summer solstice, you stop moving northward and start moving southward. So that's why it's called the solar standstill. It doesn't physically stop moving, but its northward motion stops and changes into southward motion. Anyway, between the vernal and autumnal equinoxes lie two other significant locations on the ecliptic. The point on the ecliptic farthest north of the celestial equator is called the summer solstice. And it is at this point that the summer solstice that the sun stops moving northward on the celestial sphere, as I just mentioned. At this point, the sun is as far north of the celestial equator as it can get. It marks the location of the sun at the moment summer begins in the northern hemisphere on about June 21st. At the beginning of the northern hemisphere's winter, on about December 21st, the sun is farthest south of the celestial equator at a point called the winter solstice. You can see that again at the bottom of the image there on the left. The June solstice, or the summer solstice, occurs on the day on which the sun follows its longest and highest path through the northern hemisphere sky. It is therefore the day on which the sun rises and sets farther to the north than on any other day of the year, and on which the day the noon sun reaches its highest point in the northern hemisphere sky. The opposite is true on the day of the December or winter solstice, when the sun rises and sets farthest to the south and the noon sun is lower in the northern hemisphere sky than on any other day of the year. So that's a mouthful of information, but the idea is the sun is high in the sky in the summer solstice and low in the sky at the winter solstice. And you'll see this come about in the next slide as well. So, because the sun's position on the celestial sphere varies slowly over the course of a year, its daily path across the sky, which is due to Earth's rotation, also varies with the seasons. On the first day of spring or the first day of fall, when the sun is at one of the equinoxes, that being March 21st or September 22nd, the sun rises directly in the east and sets directly in the west, which you can see here in the middle. So we, on either March 21st or September 22nd, either of the equinoxes, the sun rises directly to the east, sets directly to the west. On the first day, when the northern hemisphere is tilted away from the sun and it is winter in the northern hemisphere, the sun rises in the southeast. So we can see that kind of happening down here in the winter solstice area, where it's December 21st. The sun is now rising in the southeast, and Daylight lasts for fewer than 12 hours as the sun skims lower over the southern horizon and sets in the southwest. Right, so we can see that happening here. The path that it takes across the sky is shorter, right, because it's at a lower angle to the sky. So this is the lowest that the noon sun will get. On the other side of things, June, during the summer time, and this is the summer solstice, the sun actually rises in the northeast, and it reaches very far in the northerly skies, very high in the skies, and we get pretty direct heating, right? So during the middle of the day, the sun is almost directly overhead to us, so we get lots of heating. And it also takes the longest path. Notice how much longer this path is here compared to that during the winter solstice. So we get more direct sunlight, and the path is longer, which means we have longer days and more heating. So there's a lot of things going on in this image, and it's a great image to refer to kind of put everything together. So the image that you see here is a composite photograph that shows images of the sun taken at the same time of morning and from the exact same spot at roughly 7 to 11 day intervals over the course of a year. So this is actual photos, but put together of the sun over a course of a year. The photo looks eastward, so the north is to the left and south is to the right. So north is over here, south is over here. Because this location is in the northern hemisphere, the sun images that are high and to the north represent times near the summer solstice, right? So it's high in the sky and it's toward the north. So again, I'm going to go back a second. It's high in the sky and it's toward the north. So you can see that this is close to summertime, which is indeed true. So that represents times near the summer solstice, and the images that are lower and to the south down here represent times near the winter solstice, when the sun only gets, it doesn't get too high in the sky, so you don't get that direct sunlight. So you can see, though, that this makes a unique shape. So over the course of a year, the sun traces out what we would consider to be a figure-8 shape, which we in astronomy call the analemma. This arises from a combination of Earth's axial tilt and its varying speed as it orbits the sun. So we get a pretty unique shape. Now, in your labs, if you're in my class, you will have a lab that deals with this. And you'll see that the shape isn't always a figure-8 for all planets. It depends on the tilt and on the speed that it's moving. So that shape can vary a little bit. All right, so the closer you get to the North Pole, the shorter the winter days and the longer the winter nights. In fact, anywhere within 23.5 degrees of the North Pole, that is, let's just say anywhere within 23.5 degrees of the North Pole, the sun is below the horizon for 24 continuous hours at least one day of the year. The circle around Earth at 66.5 degrees north latitude is called the Arctic Circle. If you have our textbook, which is Universe, you can refer to image 2-17 for that. The corresponding region around the South Pole is bounded by the Arctic Circle at 66.5 degrees south latitude. So that is the Antarctic Circle. At the time of the winter solstice, explorers south of the Antarctic Circle enjoy the midnight sun, or 24 hours of continuous daylight, which you can actually see in this image here. This is a 24-hour example of the sun at such a time. You can see that the sun never actually sets if you're within that 23.5 degrees of the pole. So maybe in the North Pole, it's continually dark for 24 hours, but if you're in the Antarctic Circle, you have continuous daylight. So the variations of the seasons are much less pronounced closer to the equator. So you don't get this kind of extreme thing happening if you're near the equator, kind of like us. We never get this happening where we live here in Durant. Between the Tropic of Capricorn, which is 23.5 degrees south latitude, and the Tropic of Cancer, which is 23.5 degrees north latitude, that is 23.5 degrees north or south of the equator, the sun is directly overhead, that is, at the zenith, at high noon at least one day per year. Outside of the tropics, the sun is never directly overhead. So you can see that happening in these images here. So let's just take a moment to kind of review this. This is a really great image, but there is a lot going on. So let's just say it's the winter solstice. So the northern hemisphere is tilted away from the sun, which is imagined to be right here in the center. So the northern hemisphere is tilted away. What you'll notice is these sun rays coming perpendicular or horizontally in will hit the Earth's surface, but that only happens to some extent. If you go too far, say the next sun rays right here, it doesn't hit the Earth's surface up here. So anywhere within this Arctic circle, you will get continuous darkness for at least one day in the winter. And the opposite is true in the southern hemisphere. There's a region down here where sunlight will always hit the locations inside of the Antarctic Circle for at least one day of the year. Anywhere in between, you get some variation of that. And if you're within the Tropic of Cancer and the Tropic of Capricorn, the sun will be directly overhead at least once per year. So imagine taking this and rotating it around the sun. At some point, you will have a sun directly over your head if you're in between the tropics. And again, the opposite is true on the other side of things. So you don't really need to discuss it in any more detail. It's just the opposite case. But regardless, this is all very important. So you can put all this together and see just, for example, how these things can occur. So something as amazing as the sun never setting, it's very exotic to us because we don't ever get that happening, can be explained actually quite simply. We're tilted away from the sun, so some regions might never see the sun for a day, and the opposite is true in the south, or vice versa. So let's end this lecture with a concept check. So you can refer to some of the previous slides as you think about this, but how often each year does an observer standing on the Earth's equator experience no shadow during the noontime sun? So think about that for a moment, pause your video, and return when you are ready. All right, well, in order to cast no shadow, you should know that that would mean that the sun must be directly overhead. So this question is basically asking, how often is the sun directly overhead if you're at the equator? Well, as the sun's position on the celestial sphere slowly moves back and forth between the northern and southern solstice points over the course of a year, the noontime sun will be directly overhead for an observer at the equator only twice per year at those two equinoxes. So you could actually go back to, I think this image will make it the most easy for you. So we're asking how many times, if you're at the equator, so along this blue path, how many times is the sun directly overhead? Well, that only happens at the two equinoxes. That's the only time when you're on the equator that the sun would be directly above you, and vice versa. So a nice question to finish things off. So this was our lecture on the reason for the seasons. It's fairly simple overall. I mean, the basic idea is just that the Earth is tilted, and because of that tilt, we get the seasons. Now, in our next lecture, we're going to talk about the moon a little bit. So the motions of the moon and what's going on with that. We'll talk about things like solar and lunar eclipses and all that kind of good stuff. So, as always, thanks for watching, and I'll see you in the next video.